Well, why don't we get started? My name is Lowell Gustafson. On behalf of the International Big History Association, I am very pleased for those who are able to be here live, and for those who will be watching a recording of this later on, I welcome you just as well. Um, Everyone who's familiar with big history knows how energy flows have long been central to the epic of evolution and big history, as has been the case for many years. But we're very grateful tonight that Max Barnett is going to be examining them in light of his new research. He's a PhD student who's working under Professor David Christian in the Department of History and Archaeology at Macquarie University in Sydney, Australia. Max is a member of the International Big History Association. He's part of the Global Research Group, which is focusing on how understandings of the past can be used to inform approaches to the present and future global challenges. He's recently presented papers entitled Breaking the Cycle, Alternative Complexity Outcomes for Human Societies, and the Weights and Measures of World History. He currently teaches and aids in curriculum development in the fields of law and world history. He's graduated with a master's of research in history, and he writes on fields of demography, geography, anthropology, world history, and future studies. The current working title for his PhD dissertation is The Fork in the Road, Mapping Alternative Responses of Human Societies to the Threat of Collapse. So, Max, I'm delighted to welcome you. Thank you for making your presentation, and I'm going to try to get off the stage, and the mic is all yours.
All right. Lowell, thank you very much for the wonderful introduction and for the invitation for me to present. I am going to share my slides. For those of you that are in the chat, we were discussing earlier, if you click the full screen icon in the top right of the view, then you should be able to see. They're a bit hard to read if they're not in full screen. And close the chat as well. So as Lowell said, I'm working under David Christian in the field of big history. I primarily work with human societies, but a big part of my focus is the role of energy flows in complexity. Today, I'm going to be talking about the possibility of energy being the kind of universal currency of complexity. Interdisciplinary scholar Vaclav Smil made a claim that energy is the universal currency. So that is the kind of main thing that I'm going to be testing today. So there's kind of four goals of this webinar. The first is to test the claim that energy is the only universal currency of the universe. We're going to try and understand energy's place in the defining and mapping of complexity within the big history story. And a big focus as well is going to be on something that a lot of people are familiar with, or at least have had some interaction with, which is Eric Chason's claim that this idea of free energy rate density is the best single measure of complexity. Now, I'm going to argue today that is a kind of qualified yes, but it's helpful to kind of clarify free energy rate density numbers with ideas of interconnectivity and emergence. And the last thing that I just want to make sure that I'm doing is acknowledging that this is the kind of field that we work in big history is, while it's an academic field, it's also a field that we have a lot of educators in, high school educators. And so today I'm going to be trying to produce an academically rigorous discussion, but do it in kind of understandable terms that hopefully people can then pass on to their students. All right, so to start with, we need to talk about what energy is. Now, there's been some work recently by some physicists called Silverberg and Eischen in 2020, which argued that energy is actually the fundamental building block of the universe, and that all matter is in fact made up of fragments of energy, that matter is just condensed energy. This is going to be a debate that's been around physics for a little while already, but it seems to be becoming clearer and clearer that energy is kind of at the heart of everything in the universe, at least at the classical physics level. And I'll talk about the quantum problem a little bit later on, but things tend to break down at the quantum level. All right, so what is energy? Well, fundamentally, it is the ability to perform work. Now, work, in a kind of circular definition, is the energy transfer which occurs when force is exerted to move an object, right? So to move something, you need energy, okay? And if nothing moves, nothing happens, right? So any kind of history, big history, world history, or whatever part of the universe you're talking about, nothing happens if nothing moves, okay? If the universe is static, then nothing has happened, right? So the way that we measure energy and work, they're kind of the circle of the same thing. We measure it in ergs and joules, okay? Ergs and joules are both measurements of the same thing. 1 joule is just equal, or rather 10 million ergs is equal to 1 joule, right? So ergs is just a smaller measurement. Power is the amount of work produced per second, okay? It's also known as watts, all right? It's just joules per second. And then power density is how much. We're going to be talking about density a lot today, and I'll talk about why that's important in a little bit. But power density is the amount of watts per kilogram flowing through the system. The only difference, for those of you that are familiar with physics, between power density and free energy rate density is that the measurements are smaller with free energy rate density, or FERD. We're using ergs per gram per second rather than watts per kilogram. And remember, watts are joules per second, right? So that's really the only distinction between the two. And we use free energy rate density because it's a little bit more precise and allows us to move down to smaller systems than we would be able to with watts. So what all this means in practice is that nothing can happen without energy. Nothing can happen without work, okay? No water molecules, no stars can form, no brain can think, no jet plane can take flight without energy. But put in the converse, the more energy that's being used, the more is happening, all right? So here's kind of a process of how energy conversion would work, okay? So we put in energy, free energy, which is then converted by the system into useful output energy, i.e. work, and wasted output energy, all right, usually heat. This is essentially a very simplified version of entropy. It's not exactly what entropy is, but I'm not going to go into that today. But basically, every time you put free energy into a system, some of it gets converted to work and some of it gets converted to heat, right? And different types of energy have different conversion rates, which I'll talk about a little bit later as well. Okay, so if energy is required for anything to happen, does that mean that energy means more complexity? More energy means more complexity. Well, that's the kind of big question of today. Let's talk about quickly what complexity means. Those of you that are working in the academic field, on the academic side of big history, will be well aware of what a vexed discussion this topic is. I think at this stage, it's kind of a bit of an agree to disagree. I think it's important at the start of any discussion about complexity for at least us to kind of put our foundation, talk about how we define complexity. But it should always and usually includes a discussion of 3 factors, which is energy flows, interconnections between building blocks or constituent parts, which sometimes includes a degree of self-organization, and emergent properties, right? The debate is more about, and emergent properties can often include stuff like information. The discussion tends to be more about the degree in which each of these should be, or the weight should be given to each of these. Right, I'm going to argue later that stable energy flows, or stable free energy rate density, clarified by the interconnectivity and emergence, remains the best available mechanism for indicating complexity. But before I do this, I want to engage with the kind of more radical argument, right? I'm kind of suggesting that the energy flows does need to be clarified still. Before I do this, I want to talk about this kind of radical argument about energy presented by Eric Chason. Okay, so just a kind of reminder on free energy rate density. It is the amount of work occurring per gram of a system per second. Okay, now density is really important because some very non-complex things, like a star, produce a lot of energy, right? But because they're so big, that's what makes them produce. By virtue of their size, they're producing a lot of energy, rather than because they have a high level of complexity and have a high level of energy density, right? If I blew a human brain up to the size of a sun, the density or the amount of energy produced by that brain would be much higher, right? So a human brain has a much higher energy density than a sun, and as a result is much more complex. Now, Chason argues that free energy rate density is the best single measure of complexity. He acknowledges that it's not the only possible measure. He does talk about ideas of negative entropy or negentropy, and also about information. But he suggests that both those, that negative entropy can be kind of dealt with third anyway, and that information is too difficult to measure accurately to really be a meaningful measure. And he also suggests that information might be just another form of energy anyway. The great thing about energy is it's easily defined and pretty easily measured. I'll talk about how to measure it in a second. So I guess the big question for today is it the best single measure of complexity? To test this hypothesis, we need to determine first whether the kind of third measurements line up with other models of big history, both our kind of intuitive perception of complexity and with other discussions. So here are some models of big history that have been presented over the last sort of 2 decades. Chason one is at the side. On the left there, and in brackets are the various third measurements for different systems. Okay, you can see the benefit of using ergs per gram per second. We don't have these tiny little decimal points, right? A star has a third of 2, and then a modern human society has a third of 500,000. Now, there's all sorts of problems with how to measure this, which I'll talk about later on. I'm not going to go through all of these models, right? We've got David Christian's threshold model, Spear's levels of complexity model, and then Tyler Bock's most recent one in the Journal of Big History, which also uses kind of a levels nested levels based approach. We can see here that for the most part, right, Chason's model lines up with the other models of complexity. Okay, right? Particles to stars, to kind of planet Earth, life, humans, right? So, at the very least, it seems like third measurements line up with our intuitive and other models of complexity. So that's good. It's a good start. Now, let's talk about some of the challenges that are created by this kind of free energy rate density approach. And these challenges kind of have workarounds and solutions, hopefully. So I'm going to suggest some workarounds for these challenges. All right, so the big question of free energy rate density is how to measure it. Put simply, okay, so you've got to work out how much energy is going through, how much energy is going into the system each second, okay, so how much hydrogen a star is burning, how much food an animal is eating, how many fossil fuels and renewables modern human society is burning per second, okay, and then you've got to multiply it by this thing called energy conversion rate. So, to go back to every type of energy has this thing called an energy conversion rate. All right. When you burn something, okay, such as coal or wood or metabolize food or burn hydrogen, whatever it is that you're using, some of that energy is converted into heat, which is useless for the most part, unless you want to heat your house. Okay. The amount of energy is lost depends on the type of material used. One of the big things that made the Industrial Revolution so revolutionary was that humans started burning coal, right? Coal has a much better energy conversion rate, i.e., a greater percentage of coal is converted into work than burning something like wood or even when we metabolize food. Okay. So what this will kind of create is it lets us know that that top part works out basically how much work has been performed. Okay, what percentage of that gross energy input gets converted into work? All right, and then we just divide it by the mass of the system in grams. That sounds lovely and simple. If this was what complexity was, our job as big historians would be very easy. Now, it's pretty easy to measure the energy flow or the energy rate density of a star. Okay, it's burning one type of fuel, hydrogen, or fusing one type of fuel, hydrogen, and you can just look at the luminosity of the star to work out its energy flows. Same with biological organisms. We work out what food they're eating and their metabolic rate, and again, we can convert it. Even human societies, in terms of the type of energy they're using, it's pretty simple until you get to industrial societies, right? It's just the food the humans are producing. In industrial societies, right, humans also eat food, right? We still need food. But because of how much more energy is produced from fossil fuels and renewables, the amount of energy we actually get from food is kind of irrelevant. So you can just or is so small that it's almost irrelevant, that you can just measure kind of the like kilowattage. Industrial societies literally release kilowattage statistics each year. So it is as simple as converting that to ergs for free energy rate density. The real challenge with human societies, and this relates to a critique presented by Fred Speer when Eric Chason was first kind of discussing this stuff, is how we measure the grams of the system in human societies. If we include all the machines that we use, which is what the coal is powering, it's not powering us, right? You can't eat coal. If we include all the machines that we use, or even the planet that we now kind of control through the Anthropocene, then the energy density of human societies is significantly diluted. And this can lead to like a reading that then suggests that human societies aren't as complex as they are under other models. So the workaround which Eric Chason kind of suggests obliquely, and which I think is kind of, it's not ideal, but I think it's the best approach, or the least worst approach that we have at the moment, is to just measure human energy flows per capita. Humans are the ones gaining the benefit of the energy flows, and so the mass should just be the humans themselves rather than all of their extraneous stuff. Until the mechanical systems start working for themselves, okay, so AI or something like that, until that occurs, I think the per capita approach is the best one we have, right? It's the best workaround that we have. All right, so second problem, the thermonuclear bomb problem. This kind of is about this is kind of about big explosions and unsustainable spikes of energy flows, right? So the best example, or one of the best examples, is a nuclear bomb. Okay, so in 1961, the Soviets dropped RDS-220, that's also known as Tsar Bomba, on an uninhabited island in the Arctic Ocean. The 50 megaton explosion was 3,800 times larger than the Hiroshima bomb. If we stuck a third thermometer in the Soviet Union at 11:32 a.m. on the 30th of October in 1961, it would read as the most complex society and probably the most complex system ever, if we're using that per capita measurement. But we know intuitively, and using other models, that the USSR is not the most complex society ever. That probably goes to something a little bit more modern post-internet age, arguably global human society. This kind of problem reflects itself in other systems, right? A bird in flight is metabolizing more energy than one at rest, yet it's no more complex. A supernova is no more complex than a stable star, right? Now, Eric Chason notes these problems and notes that systems that are kind of close to collapse or just beginning or existing for a very short time can often have very, very large energy flows, much larger than they would be able to sustain, right? The workaround for this is actually pretty simple. The solution is stable energy flows. Okay, for energy flows or for FERD to represent complexity effectively, they need to be measured over an extended period of time. Now, this doesn't need to be too long. Okay, the length of time that I've found is a few data points over the course of about a 10-year period, or at least over the lifetime of the system, if it's shorter than that. And then for something that's got a really long lifetime, okay, I'm keeping in mind I'm working with human societies, so 10 years works pretty well. But if it's got a really long lifetime, something like a star, then maybe that average needs to be a bit longer. But it's about measuring the stable free energy rate density to kind of offset these thermonuclear blasts. All right. The third problem of FERD is to do with the quantum realm. I kind of flagged this a bit earlier. Big history itself, the story does discuss quantum physics. It does discuss the quantum realm, but as with classical physics itself, the big history story doesn't deal very well with quantum problems. And most of our discussions of complexity and energy break down in the quantum world. There's arguments about electrons, for example, having negative energy flows, all sorts of things. It can be argued that atoms have no energy flows at all because they're balanced between electrons and protons. And what this kind of means in practice is that any measure of complexity, I don't think this is just exclusive to energy. I think any measure of complexity kind of starts to break down in the quantum realm. So if we're going to start somewhere, we probably have to start at atoms for measuring complexity, and that result is kind of going to be almost tending towards zero, if not zero itself. All right, so to kind of summarize where we've gotten so far, right, there are some kind of problems with FERD, but most of them can be dealt with this kind of, as long as we're dealing in the classical realm outside the subatomic realm, or in the kind of the macro realm outside the subatomic world, and talking about stable energy flows with that kind of workaround for humans in the per capita sense. most of the problems can be solved by little workarounds like this. There are, however, some potential limitations. These are things that I think are a bit harder to solve with tweaking the way we calculate third. So this is a picture of the first picture that NASA has managed to take of a black hole. It's a long way away. Understandably, it's in the center of the Milky Way. It's understandably a little bit blurry. But it relates to the possibility, the theoretical possibility, for a system to have a very high and stable third, but low complexity. Now, it's actually quite hard to think of concrete examples for this that I can provide evidence for. A possibility might be a very condensed dwarf star, but that burns itself out reasonably quickly. So it may be just a case of extending the kind of average, the stable period for a bit longer for stars. The other one could be a black hole. It could fit the category of having very high energy but very low complexity. The short answer is we don't know with black holes. We don't know enough about them, but this is a possibility. So to entertain this theoretical possibility, what is missing in these systems that have high third, these theoretical systems that have high third but low complexity, is diversity of constituent parts, right? So a condensed dwarf star will still only be made of one constituent part, which would be hydrogen, maybe a little bit of helium. And so there's no diversity of interconnections between those parts or of the parts themselves. So this, those of you that are familiar with Fred Spear's work, leads into his model of complexity, which is suggesting that complexity is actually equal to the number and diversity of building blocks, what I'm calling constituent parts. I'm just using David Christian's language rather than Fred's, but they are essentially the same thing, plus the number of diversity, the number and diversity of interconnections between those building blocks. So the number of diversity building blocks plus the number and diversity of interconnections between those building blocks. Right, the higher the number of and diversity of both, the more complex the system. So because this kind of leads into, it kind of makes sense in terms of complexity as essentially a measure of structural intricacy of the system, right? The more connected the system, the more complex it is likely to be. And I think the big challenge of this approach is actually that it's kind of, particularly in more complex systems, there's no quantitative way of measuring it. It's really hard to define what an interconnection is. All right. Both kind of building blocks and interconnections differ between systems. And so there's kind of a bit of a lack of kind of consistency between the different types. I think, however, that just to kind of return to third, while third on its own is a really free energy rate density on its own is a pretty reliable indicator, clarifying it with this kind of at least a qualitative assessment of interconnectivity and structure adds weight to the argument of increased complexity, right? It avoids this kind of amorphous blob of energy problem. As I said, at this stage, it's theoretical. We'll potentially discuss in the discussion section at the end whether there are some examples that people can think of. All right. So the second problem is in relation to emergent properties, or limitation is in relation to emergent properties. So this is a restaurant that someone has built, South America, I think, of a jet, using a crashed jet plane. Emergent properties are properties of a system that only appear when a system is arranged in a specific way. So I can grab a scrap heap filled with the materials of a jet plane, stick it all together. I can even have a jet engine kind of attached to all these materials, I can pump all the energy I want, all the fuel I want through that jet engine, but it will only take flight if all of the components are arranged in the correct way, right? So if it's arranged as a jet plane and then I pump fuel into it, it will take flight, right? So the theoretical problem that this deals with is actually to do with the possibility of a system working out ways to use energy more efficient, using emergent properties that either store the energy, bank the energy, or have strategies for kind of exchanging information that means that energy doesn't need to be burnt relearning the information each time. So examples of this are, let's say, a ground mammal has adapted the emergent property of digging a burrow, so they do not have to spend energy each night looking for somewhere to sleep. Over the course of that animal's lifetime, they will have actually used less energy than they otherwise would have done. The same thing happens with human buildings, right? We build houses so we don't have to walk around looking for shelter each night. It costs a lot of energy to build these at the start, but once they're built, they stay there, okay? Sometimes in the case of some human monuments for thousands of years, right? What this means is that we're not spending energy all the time, that theoretically at least, our roads, our buildings should reduce the amount of energy flowing through our system in the long term. The other thing that can do this is information. So DNA and human information systems, writing, the internet, mean that we don't have to spend energy gathering information. It's much more easily accessible. This should, at least theoretically, reduce the emergent, should reduce the amount of energy that we're using. What this means in practice, theoretically, again, and I'm going to come back to the practicalness of this at the end, but what this means, at least theoretically, is that more emergence could lead to a reduced third reading, right? And given that emergence is often kind of stated as a feature of complexity, this kind of flies in the face of different models, right? So to kind of tie all this together, right, I suggested that energy is a key part of complexity and the big history story, and we can debate the extent to which it is a part of the story. I think stable energy flows, if we're going to pick a single measure, stable energy flows are the closest thing we have to a currency of complexity. I think Vaclav is right in saying that energy, if it not is the only universal currency, it's certainly the closest thing we have to it. But as I've discussed earlier, having in this kind of limitation system, that having clarification with interconnectivity and emergent properties provides a bit of a kind of way of dealing with some theoretical problems of free energy rate density. I guess just to finish off, I think the thing that I would like people to kind of go away from this thinking about is this. Every kind of, when I started working on third, every fiber of my kind of academic brain resisted the idea that there could be a single measure of complexity, or at least an ideal single measure of complexity, right? It goes against most of our instincts. There seems to be some theoretical problems with free energy rate density, and there certainly are some problems with measuring it in human societies. But in terms of the way that it plays out in practice, there's, as I said, I mentioned some theoretical problems, but in terms of the way plays out in practice, it's actually really hard to find long-term stable, like systems with long-term stable energy flows that buck the trend of other models of complexity, right? And I'm happy to kind of hear, and I would love to hear some examples if people can think of them in the audience as part of the discussion. But it certainly seems that as free energy rate density increases, so too do the other metrics of complexity. In some senses, it means then that we're trying to prove a negative, that free energy rate density is not kind of a measure or not the measure of complexity. And I think that's the challenging part about it. I think at the very least, if you're not willing to buy Chason's more radical argument, that third is the kind of core measure of complexity, then certainly this kind of idea of free energy rate density clarified by interconnectivity and emergence remains a very convincing one. But yeah, I'd love to hear what people think. And if people have any examples from, we've got lots of different areas of expertise, if people have any examples of systems which have very high energy density, but low kind of complexity by other metrics. All right, so I might finish it there, but I hope people have got a kind of good understanding of energy flows and the way that it plays out through the course of big history. But we might throw it out to discussion now.
It's all yours, Ken.
Okay, sorry. It looks like it disconnected. Sorry. By chance, I have written a critique of Eric Chazon's book, and my background would not be one who would seem to be to challenge what he has to write, because he's a physicist and I'm a physician and a philosophy and have a philosophy degree as well. But actually, that background did give me some insights as to some fundamental errors that were made in the book. And it's still appropriate for this discussion. Number one, it's really important to have a good definition or characterization of what a complex system is. I'll try to summarize things rather than go through my whole paper that I've written for hopefully an upcoming journal. But number one, his definition was very non-specific, which meant a lot of things were included that are not considered complex systems by anybody in complexity science that I can find. For example, computer chips, they're not complex, they're complicated, but they don't meet anybody's definition. And they have high energy flow. So he came to the contrary conclusion that a vacuum tube computer, for example, had to be more complex than a computer chip, an integrated circuit computer chip, because it used more energy. But obviously there's a question of efficiency, as I think you pointed out. There's a lot of wasted energy with vacuum tubes. And of course, computer chips, he also said, are more complex than brains because it has a higher FERD than a brain. But again, you have to worry about efficiency. Second of all, so there's a problem with sensitivity versus specificity of your definition. And, the more criteria that a complex system meets, like indeterminacy, number of interacting components, which is another way of information. Information is still very fundamental, what constitutes a complex system. So like you said, you have a lot of energy out there. It's doing a lot of work moving particles around, but it's not doing anything interesting. It's not complex. So you're right, information or a number of components and how they interact. The human brain's the most complex thing we know of. You get more and more of the characteristics of what a complex system is. And in one of my papers, I think it lists about 7. Number 2, the most serious error made in the book is a tautological error. circular argument. He essentially repeated, well, not always, but frequently would say, well, this uses more energy, so it must be more complex. You can't start out, and this happens in medicine all the time, so I'm aware of it. You can't start out with a metric or a diagnosis, a new test for diagnosing a disease and say, I'm going to use that test as my gold standard. You got to first determine if it is a gold standard by comparing it to other metrics. So he comes up with some counterintuitive examples, like a plant that uses C4 photosynthesis, or coal even. Coal is more complex than wood because it puts more energy out. Well, if you use that line of reasoning, it turns out natural gas is more FERD than coal. But gas is very non-complex in structure. It's the opposite, of complexity. And so those are two big ones. And then the final error that's made in the book sometimes is, less commonly, is selection bias. You can't choose your numbers to fit your hypothesis. So the galaxy is a good example. He says our sun, I think, is about 5 ergs per gram per second, whereas the galaxy overall is about three or something. But it turns out red dwarfs are 75 to 80% of the stars, and they have a less energy net FERD than the galaxy does on average. And of course, the galaxy intuitively is more complex because, the stars themselves are part of the constituency of a galaxy, and a galaxy has nebulas and black holes and poles. Well, they used to have poles, or excuse me, sorry, cold. So anyway, those are fundamental problems with the book on the logic. I won't argue the physics. I'm not qualified, but the logic I am qualified to critique. And there's some fundamental errors made for that reason. You're right. In complexity science, they have not come up with a good metric. That's Seth Lloyd has 43 listed. And he didn't actually include Chazons. I actually wrote him, and he said, okay, yeah, that's an element that should be included. So nobody's come up with a good metric. Everybody else just about, though, does include some form of information. Chazon's unique in using energy rate flows, and I think, energy is serving information, all the interactions. The more interactions you have, the more energy it takes to drive it, also to thwart entropy, to keep all those constituents working within a phase space where the complex system is still functional. So I think I've probably taken up enough, but those are some of my comments. I do agree. Thank you what you're bringing. And certainly there are limitations when we get to the quantum realm and other extraordinary circumstances like black holes.
Yeah, thanks, Ken. I don't know if I'll be able to address everything that you said, but I think a couple of things, and this sort of relates to Paul's question about dynamic kinetic stability as well, to some extent, that defining the boundaries of the system often kind of causes the problem, rather than the process itself. On the kind of computer chip discussion, I'm not sure whether Chason would argue. Perhaps he's written a lot of books, so his kind of argument has evolved a bit over time. But certainly, I would not argue that a computer chip fits as a system on its own until it becomes like it's part of the human system, until it becomes kind of artificial intelligence, in which case then we measure it on its own merit. So, I mean, that kind of perhaps becomes, and that's kind of the quibble that Fred Spear had, that you're taking a little bit of liberty, perhaps, with the human system. But, a computer chip or a vacuum cleaner or anything else on its own is not really a system on its own. It requires a kind of external amount of energy, someone to actively put energy through it, whether it from a coal power plant or whatever else that powers our computer chips. So yeah, on its own, it's high energy but not very complex. But the system that it fits into allows it to it's kind of an emergent property of a broader human system. I think the thing about stars and galaxies was kind of interesting, and again is a bit of a kind of common discussion. But I will say that let me just pull the slide up again of the different. Just pull this up again. Where is it here? These tables. I will say that even kind of the non-third approach to big history tends to put galaxies in the less complex category than stars. So whether it's a red dwarf or our sun, the third of the star should be higher. It should always come out higher than the galaxy. But I kind of take what you were saying about the red dwarf possibly having a lower energy density than galaxies. It kind of comes down, I think, to, again, this problem of defining a system rather than like defining the boundaries of the system of the galaxy rather than anything else. You know, do you include the vacuum of the system or what? Or the matter floating around in the vacuum or not?
Okay, well, thank you, Ken and Max. In this airmeet system, here's Dave Lepore. Good.
Okay, very good. Thanks, Max. That was a very nice talk. And I think it brought a lot of good questions. And the one question that I really liked was kind of near the end, where you say that things might become more energy efficient, but that kind of goes against kind of becoming more of a higher third to it. And I don't have a answer to that. But I mean, it's something to really think about. And in environmental economics, there's something called the Jevons effect or paradox. And that is whenever the government or technology makes like energy more efficient, usually the more energy or the resources being used, right? There's just, once you have something that's more efficient, there's just more things that you can apply it to. And so that's just a bigger, system, not necessarily a more dense system. But I was wondering, what other approaches might you take to look into that question?
Thanks, David. Yeah, I mean, I think, and here's the really interesting thing about emergence, is that they all seem to create these more efficient approaches. And I mean, the kind of the example that you gave of the kind of corporate R&D, the corporate R&D department, we found this new great way to save energy, and in the process we spent all this extra energy. I actually think that's a really good metaphor for what seems to actually happen. That somehow, despite all these kind of new developments in energy efficiency, that it just provides then a baseline for the system to get more complex and burn more energy doing other stuff. There's sort of very few emergent properties that lead to lower energy flows in the long term or decomplexification in the long term. But I would say that if the emergent property does lead to long-term reduced energy flows, we would normally attribute that to also being a decomplexification. So an example would be the virus. Right, viruses have evolved to actually to use less energy. Right, they're parasitic, but they used to have a kind of nucleus and used to have a cell, and now they don't. Okay, they use less energy, but we also would argue that they're less complex. Right, they've got less interconnections. Whatever metric you use, their emergent property is to become less complex as part of that process. And you've just reminded me as well to kind of address something that Ken said in terms of presupposing that more energy means more complexity. I think it's really important when we're considering any of these discussions, and I think Ken kind of identified this well, that We need to look at the different metrics of complexity and whether it fits in, rather than saying, well, more energy means more complexity, right? That's Jason's argument. That's kind of my argument. But lining it up with the other system, the other metrics of big history is really important as well.
Very good. Thank you.
Thanks very much, Max. This is fascinating stuff, and it brings up all kinds of questions. I'm a little reluctant to ask this question, but I've been studying complex systems for about 25 years now.
Yep.
And I wonder, has anyone sat down and worked out the question of the limitation of taking a quantitative approach to complexity? It seems to me that complexity is largely a matter of qualitative issues. And I find a quantitative approach almost seductively pulling me away from what I think is really important, especially the issues of information and structure. So I just wanted to throw that out. When I started working on complexity theory, people told me there were at least 30 definitions of it, and as far as I can tell now, there are a whole lot more. But this was just an issue that this all kicked up on me. Thank you.
Yeah, thanks, Ken. I think it's kind of an ongoing fixed question in terms of the value of. I think rather than saying that there's kind of barking up the wrong tree to say that we should be going for a qualitative or quantitative approach. I think we just need to recognize that each has their own limitations. I think, and I've kind of talked about this today already, that even with the kind of quantitative, potential quantitative benefits of free energy rate density, there's so many kind of outlier cases that need to be clarified with qualitative discussion about emergence, information, interconnectivity, that I'm less convinced by kind of the energy as the one and only be all and end all of complexity. I think it always needs to be clarified with some qualitative discussion. I think there's also a question of how realistic it is to get, anything more than an estimate of energy density, particularly in more complex systems. The kind of the tangled net of measuring complexity in human societies, for example, means that you're not really getting a perfect measurement anyway. It's more of a qualitative indicator of something going up. So I think the point where we stop and say, no, we need to get an exact number for each system is probably the point that's gone too far. I think having a kind of estimate, often based on more qualitative indicators than anything, or a combination of quant and qual, is actually kind of the approach to take. Qual doesn't kind of have enough meat on the bones and clarity around it, whereas I think quantitative is can be kind of too prescriptive. So finding a balance, I think, would be my approach.
Thank you.
Oh, hi. I'm just had a question about the quantitative.
Yeah.
Basically, I specialize in creating data visualizations, and I've done this with data from Chronozoom, and always interested in looking at other data sets. And I was just wondering if there were data sets which describe, either estimates or whatever that we could use in our visualization. We're doing this work in augmented and virtual reality, so you can project into 3D and all that. And I just wondered if you had any data sets that would be interesting to look at from that perspective.
Yeah, that's a really good question, David. And the kind of short answer is that there are data sets, but they're very minimal, right? Again, to sort of show you the slides. Sorry, let me go into full screen here. I did put some up, but they're not very comprehensive, I think, is the main problem. So the these data sets at the side are probably kind of there's a few more, but that's kind of most of them that Chason has provided. I think, as Ken alluded to before, there's sort of some distinction between different types of stars, and you could make distinctions between an animal in flight and an animal at rest, the human brain versus the human body. So I haven't put them all on there, but there are. I think the short answer is it's kind of quite limited in terms of what we actually have. It would be reasonably easy to get measurements for simple systems. The challenge really comes in as complexity increases. But there are some graphs in Chason's book, Cosmic Evolution: The Rise of Complexity in Nature. I'll put it in the chat for you.
Yeah. Okay.
But they're just essentially kind of exponential kind of hockey stick graphs.
Okay. Right.
How they play out. They're a little bit more. They're not a straight line. There's points plotted where it kind of goes up at different rates, but it does end up looking like a hockey stick graph.
And it shows how each point is calculated, right, based on formulas like you showed.
Sorry. Here's the real problem. I think is that Eric Chason has not been particularly forthcoming with the approach, the exact approach. But to give you kind of a general, I'll just show the slides. The general formula. The short answer is the problem with measurement is it depends on which system as to which energy type it is. So you can see here that different energy types for different systems. But if you can work out, basically the thing that you need to know is this energy conversion rate. So knowing for human societies, Vaclav Smil has a really good discussion on how to calculate it for different human systems and the energy conversion rates of different energy sources. But if you understand that conversion rate, then it's pretty easy to just multiply. That's kind of the basic formula: is gross energy consumption or gross energy flows multiplied by conversion rate. And then if you want third, you just divide it by time. By mass. Okay.
Can you just put that
Yeah.
person's name in the chat?
Yeah, Vaclav Smil. I'll dig out the book for you. What's it called? It's called Energy Transitions. If you're interested in this, those two people, Chason and Smil, would be my first port of call.
Okay. Well, thank you.
Smil mostly works with human societies, and then Chason does the kind of big history stuff. There is a data set that's taken from Chason in David Christian's Maps of Time as well.
Oh, okay. Right. All right. Thank
Yeah.
you.
Chason has the kind of most complete data set.
Great.
Okay, thank you, David. Any final questions for Max? And again, the way you do that is to raise your hand. I have to ask you to do that before I can so-called bring you on stage to ask the question. Well, if not, let me thank Max for a wonderful presentation, really pushing our understanding of energy flows forward. And thank you for some very insightful questions. So I appreciate everyone's time. Thank you for this very worthwhile evening together, or afternoon, depending on where we are, I'm not sure. So thanks again, and we'll look forward to future discussions on this.
Thanks, everyone.
Okay, bye-bye now, everyone.